So now I'm going again on the transfer function definitions. I changed this to 1. And I need one oscilloscope to see the time domain signal. Okay, please do that and tell me how much is your delay time. Beginning, how much is the delay time? Apply 2-second delay for step 2 to see it better. For step source, I'm applying 2-second delay. And we want to check how much is the delay time. ببینن اصلا چجوری چند کم بودش الان میخوام بهشون بگم چیز بکنم برم سریع اومد یه جا بعدا ما اگه میگم چیز شد بعدا من ادیت کنم بفرستم حالا تعمیر So anyone could find the delay time? .3 seconds. Based on the calculation or based on your measurement? You know, okay, let's see. This is the output, this is the input. I applied input here. And the output when it reached to 50% of its final value, how much is the X? It's 3 point, almost 3, yeah. So the delay time is, how much is delay time? 1.3, yeah, it's true, yeah. Yeah, because we applied input at t equal to second, and this time is from here. How I cannot do the from here to here. In fact, from here to here. That's almost 1.3. How much is rise time? What is the definition of rise time? Almost full, yeah. Which means from here to here is the first time it reaches to final. How much is it? Almost 2.3. Yeah, maybe 2.4. How much is settling time? Let me increase the duration of simulation. When it, here is 98%, here is a bit less. It should be almost here. Almost here, yeah, because we cannot say really precise, but yeah, almost 6. Yeah. Suppose we want to, and how much is the overshoot? The peak of overshoot? Almost 5.5, yeah. And can you say at which time the peak should happen? Almost 5.5. Yeah. Suppose I want to make this system more slower. I wanna omit the overshoot. What should I do? Yes. We should increase damping factor or reduce. No, if increase, we'll have higher overshoot. Or yes, exactly. Yeah. If we increase damping factor, which means we are increasing, it's gonna be damped faster.
So how much is damping factor here now? 0.5. Yes.
0.5. Let's increase it to 2. Here, yes, and how about the poles? We are in which situation? Over damp, critically damp, or under damp? Yeah, it's in critically damp. We have a double pole. See, it's critically damp. If I put damping factor to 0.
Can you add the other one, show me together?
Oh, yeah.
For better comparison between them.
Yeah. I can have. Oh. See, we are reducing the. We are increasing delay time by reducing the overshoot. Yeah, that's kind of trade-off. If I increase damping factor, after this, I'm gonna go to, for example, 5. I'm going to overdamp. You can see it's much slower. What happens if I take the damping factor equal to 0? We don't have any damping factor, which means it's not gonna damp. Yeah, exactly. It's gonna keep oscillating. Yeah.
This is the fastest, if you can say that, in terms of the right time. But doesn't for you, doesn't work for you because it's not the same.
Yeah.
The absolute fastest is this, but useless.
In this example, how you can control the damping factor in this example? You don't want to change if you have oscillation frequency, you don't want to change the oscillation frequency. You only want to change the damping factor. Yes, exactly. This is the component that we are using that to damp the energy stored in inductor and capacitor. If I increase the capacity, the resistor, it's gonna go to which side? Toward overdamp or toward underdamp. You can't find one extreme example. If I increase that until it's gonna be infinite. When a resistor is infinite, which is open circuit. If I don't have open circuit, if I don't have any resistor there, this is gonna be that's lossless. Yeah. When I'm increasing the resistor, that is, we are going toward underdamp. Yeah. When I'm decreasing the resistor, we are going to overdamp. Yeah. You can easily find by the overshoot in lossless situation. Okay, that's I think what I. Sorry, I just wanted
It's a good time to check this things on. So please give your comment when you feel something I'm going too fast or too slow. We adjust it. Sorry. Is it okay? Yeah, if you just don't want to. So it's matter of control. I should go with the speed that you guys can follow. If I go too fast, you may not follow, or too slow, you will have some overshoot. Cannot tolerate. Okay. Okay, let's go back to here. So now we want to check the steady state to consider the steady state of the error. We want to see whether the system can follow our command at long term, at least, or will have always some error, or it cannot even follow, right? So what you do is you ask the system, are you following me, or can you follow me, by checking this error, right? So this is an example to see how it works. Let's say the transfer function of the open loop system is this GS second order, and it's inside the feedback, and then we apply the unit step, right? The unit step in the Laplace is 1s, and then we want to see how output is, how the error is actually changing over time, right? But we don't care about the transition. We just want to see at the final stage how will be the error. So we just multiply the whole transfer function by s, and then we get the limit to 0, s to 0, right? And for this case, you will see that the final error would be 0, right? So it means no matter how this system reacts to the step, I mean, in terms of the transition, this error in the time, maybe at the beginning it start to go something, but at the end we know that it go to 0. Right. So we say that this system can actually track the step and with 0 error. So the input was simple, so the system could follow. Next level, we sometimes want to see how the same system can respond to the other type of input, like the RAM, a bit more complex input, when you are keep changing the input, like linearly, right? So the RAM in S domain is what? 1 over S2, right? Just one integration of the step. You multiply it by the G of S, right? Basically, let me write the ES is this. ESS in, if you do the calculation, the ESS will be like this. G of S times the input. The input is RS. So the error would be, this is the GS. Maybe I need to. Yeah, it's over here anyway. 1 plus GS times 1 over S2 for the input, and then for the final value, we can have this S and then S to 0. If you calculate this, you will come up that the ESS is 0.2. This means what? The ESS of 0.2 is what? Is saying what? Exactly. Yes. So what you want is the input is like constantly increasing. The output at the long term, we don't care now about how the initially is changing, but the output is kind of following with certain value of error, which is 0.2 here. Always like 0.2 times of the input output, right? This system, we can tell that still can track, but with some certain remainder error. In some of the cases, this one is still acceptable. You have a system, you are seeing that the system is tracking with some error. But in the perfect case, you try to having, depending on the input. If you are using this kind of input, you really like that the output can perfectly with 0 error follow your input. But in some cases, this also acceptable. And then what if we go one step further, integrating the ramp once more time to get a parabolic input signal like this? We want to see how the system can respond to this input. This input is a bit more difficult than the simple ramp because the input is kind of get accelerated, right? So in the S domain, this signal is what? Is the integration of the ramp, right? Ramp was 1 over S square, and then once you get the integration, you should multiply once more times 1 over S. So the S domain of this signal is 1 over S3. Right? And then again, you put it to this. For the final value, you multiply it by S, and then S goes to 0. And if you solve this time, this equation, the limit will be infinity. So it means what? There is output, but the output is not, I mean, the distance between the input and output keep increasing. It cannot really follow your input. So let's say, let me clean a bit. So this input is like, there's no good space to draw. Is parabolically increasing. Your system maybe has some transient at the beginning, but it's trying to follow, but maybe cannot follow very good. So that gap is keep increasing. So at the end, it cannot follow, you can say, right? So we definitely don't like this. If we are supposed to control a system with this kind of signal at the input, we want really the output to follow. So this is kind of, we can say this is out of our control, right? It's not following. Yeah.
How we can make the error less in this step? The system, GFE, the order second. Can we reduce the error when we applying one parabolic signal to a second order system? Sorry. Okay, let's see the formula. What is important when we are setting S to 0? Yes. Right now, the problem is why S is becoming infinite. Yeah. So I need to cancel out that 1 over S.
Yes. So for this kind of input, like the parabolic input, right? In general, if you write the equation for the error, it's something like this, right? The input is 1 over S cube, and then you should multiply it by 1S and then S to 0, right? So in the numerator, you have this 1 over S2, which tends to become infinity when S goes to 0. you should somehow provide some situation for GS so that, because let's say you can manipulate the GS somehow, so that this GS provides, so maybe I write it like this: GS has some denominator, right, and some denominator. Yeah, you can. So I just give you some simple examples. So if the GS, has a part of like 1 over S2, right? Let's say I'm just trying to design. Let's say if GS is something like 1 over S2, right? If you put it here, if you put it back here, what will happen to the error? 1 over S2 plus 1 over S2. Then the limit will not be infinity anymore, because this S2 over here will be eventually cancelled, but may still have some error, not infinity, right? So in fact, in general, if you assume that GS is S2 times something, anything else, right? GS, let's say, is 1 over S2 times h of s, some other function, anything else, then this error will not be infinity for this, right? So what you need to do to improve or reduce the error for this kind of input is to, at least to confine, is to make sure that the GS, right, can have this kind of factor of 1 over S2. So these are the things that you can somehow modify.
Can make it correct.
Yep. So let's say your system is this function, but you want your system to follow this type of input. Exactly, right? Because to make sure there is
1 over S.
Yeah.
I think just that want to add 1 block.
As a system. No, we are
Each block has the transfer function of 1 over S. If you apply each mathematical function on a input, that means we need to add 1 integration in series with.
You see, if you yes.
I think we have limit error. If you want to have 0 error, what should we do? Can I write after here? That's okay. I thought here we had 1 over S2. Here, I'm sorry. It's 1 over S2 plus S2 GS. If I approach S to 0, it would be 1 over S2 G0. GS, yeah. If GS doesn't have any factor of 1 over S2, this would be infinite. Yeah. If GS has one factor of S2, alpha S2, this one would be 1 constant, 1. If GS has factor of alpha over S3, it would be 5. That's 1 over S2 GS. which is 1 over S2 multiply alpha over S3. When S approaches to 0, this one is, it would be 0, which means if I want to say have 0 steady state error, I should add two.
What? Yeah.
Sorry,
No, it's very important here because in fact, you always to reduce or minimize the error or go to 0. One way is to add the integrator, depending on the type of the signal you apply. So this system originally, let's say, go back from the step. The system itself has one integrator itself internally, right? 1 over S. So 1 over S is enough for following the unit step signal with 0 error, as we saw here, right? Because internally the system has one integrator inside. And one integrator is still enough for the system to follow the RAM with limited error. But if you want really reduce this limited error even to the 0, then it means you need to add one integrator. It means you need to add something 1 over S more to it to be able to reduce this error really to 0. And then for the other one, you need to add more integrators to really follow the parabolic or more complex signal. So this is just that quick solution that you can know. Once you want to really reduce the error, you just add an integrator. You need to, because adding the integrator, basically you are increasing the number of poles, right? So it might cause other stability issue. We will consider it later. But let's say if everything is still stable and you want to follow this kind of input, ignoring the other factors, just we are focusing on the steady state error, then it looks adding the integrator is solving the error problem. Yeah. So this is in general saying, this is actually basically saying what we are talking. This steady state, this formula is only valid when we know that the system is stable, right? Otherwise, this formula is not working. Once the system is stable, you can tell that we can use this kind of formula to easily find the final value of the error. Okay. This is again same thing, but we here having another function just here. It doesn't matter that much. It's just doing some more calculation. It's nothing new. And then okay. And then I guess these things are pretty much similar to what we had. Here is just one example. Assuming that the GS has this frequency response or estimates response, and then H of S has this. Okay, and the input is like unit step. You can calculate the final error value by just solving this Laplace domain thing, which is not new. I just going faster, just checking if there is anything new, just anything just normal, right? You multiply by 1 over S time S limit to 0, and you figure out that there is some final constant error. Could you predict that this system cannot follow or cannot really go to the zero error with the unit step based on what we had seen before? So basically, if you calculate this GS times HS is what is, I mean, is this, right? 10 over S plus 2 times S plus 3, right? Right, this is GH, right? G times H. S plus 3. So as you are seeing here, there is not any factor of S, right? So the previous example, you remember the G was 1 over S times S plus something, maybe 10, is it? Something like this. So in the previous example, we were seeing that there is 1 over S factor over in the transfer function, right? This 1 over S, as you saw, could helps for reaching zero error for the unit step. Maybe this page, right? Because of this S, here, right? In fact, this S was helping to, after the calculation, you could reach to zero error for the simple step function, right? But in the new example, GH is effective transfer function of the loop, right? And the GH doesn't have any 1 over S factor. Since it doesn't have an integrator, basically. It has some other poles, but no integrator. So since there is no integrator, it cannot even reduce the error to zero for the simple UT function. You could basically kind of saying, just by looking at the transfer function, that the error is not zero for unit step. You just need to count how many integrator the system has. The more the integrator has, then more can respond to highest order of the input with zero error. Okay. So after these things, we are go to, as a control designer, we go to see what kind of things we can do on top of the system to improve the output or control the output as we want, right? So normally we have a system. The parameters of this system is not under our control. The system has some response. It works based on its nature, right? And we want to give the command. We can manipulate the command we give, but the system we cannot change, right? The system is fixed. You can give a larger command or with a different profiles to get to get this most closely to what you want at the end, right? So one of the simplest things we can manipulate is to the command is just adding some gain to the system. This is the most simple thing that we can. So this gain is, if you add this gain, in fact, you can write the whole closed loop thing based on the gain you put in. Your gain will be doing some manipulation to full loop, right? So what will happen for the final steady state error when you add your gain? if you look at this, what you are seeing when we add this k factor, yes, the higher the gain, the lower the error, right? The higher the gain, because it's in the denominator, so the higher the gain, the final error will be less. So it means you have this your servant. This is your servant. You want to give a comment to him to do something for you, right? You can just be very kind and ask very politely, right, to do something for me. He may not give enough response to you or may not do the job you want. But if you maybe shout at him, push more stress to him, right, with a gate, you, he may follow your command better under pressure, which is not usually the case in the human system interactions, but may sometimes works right. So this is kind of the gain. You push more pressure, it might follow the output more close to what you want, right? This is the simplest thing that you can do. So here is the effect of this KP. We actually, this KP is, we call the proportional controller. Proportional is just a constant factor to the input. We call it proportional factor. So as you saw, the increase in the K reduce the steady state error, maybe increase the response speed, right? And if the system is more complex, like more pole, it increase the overshoot, right? You're asking faster to do something if the personality of the servant is more complex, it may have some overshoot, doing jobs quick, but damage something else to finally get what you want. So, and if you put too much pressure, the poor guy will be unstable, right? If you put too much pressure, since it's not a single pole, the human is not a single pole, it's very complex, so it may go to unstability region. It may not even work for you, right? So the next level of the controller, we call it derivative controller, is to manipulate the input of the system. You can add some derivative part instead of just a constant gain, right? The derivative part is doing what? Let's say if the error is not changing, the error is not changing somehow. Then when you have this derivative part, then it doesn't generate any output, right? So it means when the error is reaching to the final stage, which is not varying too much, then this block that you put it here is not generating that much of, it's not applying any input to the actual system. It means it doesn't change the system, so it feels that everything is stable. But if the error is varying fast, then this derivative is seeing the variations and amplify it and give it to the system. So in overall, this kind of improve the stability of the system, because when the error is settling down, it does not allow the out. This U of S is not changing too much, right? When the variation is at the very end, it is kind of stabilizing, doesn't change the system too much anymore. So from that perspective, it makes it more stable, and also make it more what is slower, basically, because at the very end, when everything is settling down, this is not passing anything that much to to finalize the final value, start slowing the system. So basically, this helps for improving the stability of the system. If your system is by itself is too much of instability, then maybe this helps for the stabilizing. So here is mentioned that it's kind of a braking force. So you see it reduces the overshoot and settling. And there is one problem with this derivative controllers, which is due to the noise. So all of the system has some noise from every point, and then the noise basically is unknown signals coming to your system, right? And they have different frequencies. Noise is not just DC, it has every frequency, right? So the high frequency part of the noise actually can pass through these derivatives. And then the noise will kind of get amplified. You don't want to care about the noise, but the noise is getting amplified using this derivative function. And it's corrupting your final output of the system. So because of this problem, it's not usually used alone and sensitive to the noise, we can say. And then the next controller is the integral controller. As we saw earlier, right? We sometimes it's good to have this kind of integration, adding it to improve the steady state error. So you can define some integrator here to reduce the steady state error, but adding the more pole basically is a pole at the center at the zero, right? Adding more pole may cause some other problem like overshoot or stability problem, because you are making the system with more pole and make it more complex. So combining of these kind of controllers, you can get different performance. Let's say you can add some constant gain plus some derivative controller, which we call it PD, proportional derivative controller. You can somehow get the improve the performance of better performance of the both function. So the gain can improve the initial or says initial muscle to drive the system toward the final less error, make it faster. But on the other hand, this derivative some sort of shock absorber, it says, because it tries to get break when the system is reaching to the end, right? And you can playing with this, you can actually control overshoot while you are still having a fast rise time, that kind of things. And this also helps for the noise problem, because this KP proportional path kind of control the noise generated by this. And then you can have another type like combining the proportional and the integrator together. So again, the P is reducing the rise time, make it faster. Integrator helps for reducing the steady state error. And again, still has the problem of overshoot and oscillation because of the integrator, for example. By time the controller is saturated. Yeah. So, I mean, overall, these are the basic things. Overall, combining all of these techniques is the controller. We usually call it PID, Professional Integrator Derivative. It might not be required all of these things for any system depending on the GS. If the GS has internally some integration factor, you don't need maybe have this integrator part, right? Because the transfers function of the GS already has it. So depending on the input you want to follow, the G of S, you might design these coefficients and the variables to get the best performance you want. You want to make it quick, you want to not having too much overshoot, you can control all of these things. And this table is just summarizing all of the combination of the controllers, let's say proportional, integration, integral, and derivative. And it's just summarizing, let's say for the proportional, making the system faster, the accuracy improves, but it's not perfect, right? The error still may remain. The error, we know that the integrator actually improves the error to 0, right? Every 1/s you have improves the final steady state error for higher order signals, but it might increase the oscillation risk, right? These are not sensitive to noise, but we know that the derivative is kind of sensitive to the noise because it amplifies the high frequency noise. But on the other hand, make the system a bit more stable because it slow down the system at the, let's say, final stage when it's getting settled down. And it doesn't do anything for the accuracy to get the error become 0. And then the combination of the other things, you can try to improve all of the aspects. Let's say if you combine all of these things, you can improve or optimize everything for to get a better performance at your region of operation. So for each of these things, we can give some simple examples, right, to see how you can adjust these variables to get the better performance. But at the moment, we are not going to go through some example here. Okay. You have any comment, Hassan? Maybe if you have any. Yes.
In general, if you want to make it system faster, you should use which kind of controller? Want to make it faster, you increase the gain, your right time reduce and system becomes faster. But if you make it faster, the problem is you saw maybe increase when we reduce rise time, we had overshoot. Yeah. But sometimes our system cannot overshoot. For example, pressing acceleration, you go fast and suddenly how you see when your stepper has problem, it's gonna shaking. Yeah. So you need something to just reduce the overshoot when you are increasing your speed. The response speed of the circuit. Which one can you use for reducing the overshoot and make it smoother?
Yes.
Yeah. But if you have PD, for example, you never can reach to your final speed. You will have at the end, for example, 5 kilometers If you have one steady state error, how can you compensate that? If you wanna eliminate steady state error, if that's important for you, you should use integrator. You don't want overshoot. You want to make the response smoother. You should add P, and you should add D, and for faster response, you should add P. So why we are not using all of them? Depends on, yeah, exactly. Yeah, we can use PID for all. Maybe don't do that. It's a perfect. I can see everything is put in PID. How many they have costs? If I add any of them, they have costs. They may make my system more prone to noise. I should consider more about the time when I'm adding more for that. Yeah. And at the end, it has cost them making my system more expensive. I should be careful about that. Shall we go through the next one? Oh, okay.
Maybe.
It's time. Okay, fine.
So I just give a very simple example here, just single order, because single order is easy to deal with, right? So let's say your system is just a single order. If you just use it without any controller, you give the command to, let's say, 1 over s plus 1. How is the input when you have the step? It's just one simple exponential thing, right? It's just start going and with a rise, with an exponential with a tau of 1, right? Time constant of 1. 1 minus this, basically, to the step, right? The response is like this. Right? Without any controller or without any closed loop, once you apply something to the input, it will be reaching to the final value, but with the time constant, right? The simple port, single port. But what if you put it into a feedback with just a KP, let's say the proportional? The final closed loop function will be what? Can you help me to write? No, I mean in the S domain. In the S domain, I mean the closed loop function is how? Plus 1 divided by KP over S plus 1, right? If you simplify this, we get you what? S plus 1 plus KP, right? And then KP, right? It's like this, right? Should be some. It's right here, right? Yeah. And then if you return this back to time domain, is how? Can you? Can maybe I write it on this way. You need to divide it by KP, right? The
1 over S plus alpha.
Yeah.
To power of minus. You have one gain.
No, the gain should be 1 yet, right? No, 1. Not 1. That's true. So let's say the transfer function will be like this, right? And then if you have the input of unit, what would be the response? The transfer function of closed loop is still single pole, but the pole is kind of larger, right? The pole is larger. The larger the pole means what? It means this exponential term is negative 10 times that pole, right? Right? That the exponential term without the feedback was only e to the minus t, right? Now the time constant becomes 1 over 1 plus kp, basically, right? Initially was what? Initially was only 1. Now becomes this, right? Once you increase the kp, basically you are reducing the time constant, right? So if you do not have any controller, your response is just the nature of the system. You just go with the time constant of 1. But if you increase the kp, you are able to kind of increasing the speed of the system to respond for you, right? So with this manipulation, you can actually adjust the speed even faster than what it has to be. So for the single pole is simple. You can do all of these things by hand calculations. For the second pole is still doable. For higher order becomes more complex. Because for the single pole, you are not seeing any stability issue because it still remains single pole. Just give some intuition to you. How, when we say that the proportional is helping to increase the speed, how? With a single pole example for yourself, you can get sense how it is changing. It's basically manipulating the time constant. Yeah. Okay. Maybe it's enough for today, and then we will continue tomorrow. Okay. Thanks for attending the session. See you on tomorrow. Is this time okay for you? It's fine. Yeah, let's continue on the same time. Mhm. Okay. Thank you very much. Thank you. Bye-bye. شده ببین یه چیزایی هم وسط شروع بزنم میرسه بدون مشکل. میخوام سریع برم